We're studying optics, the theory of light. And other electromagnetic waves. And last week was geometrical optics. And this week is wave optics. That's in the textbook by Bauer and Westphal, chapter 34. And the screencast will have two parts. The first part will be interference, and the second part will be diffraction. So let's review a little minute electromagnetic waves. And we've already studied geometrical optics, and now we're studying wave optics. So what's the difference between geometrical optics and wave optics? Well, here's from a Google search. Classical optics is divided into two branches: geometrical or ray optics and physical or wave optics. In geometrical optics, light is considered to travel in straight lines, while in physical optics, light is considered as an electromagnetic wave. So, an electromagnetic wave has a direction of propagation, and that's called the ray, and perpendicular planes are the wave fronts. And what we did last week was we studied the directions of the rays, and that was enough to consider reflection and refraction. In the field theory of electromagnetic waves, the equations for a plane wave in a uniform medium are E of x and t is E0 sine kx minus omega t epsilon hat. And B of x and t is B0 sine kx minus omega t k hat cross epsilon hat. E0 is the amplitude of oscillation of the electric field. B0 is the amplitude of oscillation of the magnetic field. K is the wave vector, or sometimes called the propagation vector. Omega is the angular frequency. Epsilon hat is a unit vector. It's the direction in which the electric field oscillates. So that's the polarization vector. And B is in the direction of k hat cross epsilon hat, where here k hat means the direction of propagation. So the electric field, the magnetic field, and the propagation vector form an orthogonal triad. So k is the propagation vector, epsilon is the polarization vector. The directions k hat cross epsilon form an orthogonal triad of unit vectors. So epsilon might be in this direction, k might be in this direction, and k cross epsilon would be in this direction by the right-hand rule. So here's the polarization direction. It's the direction of oscillation of the electric field. Here's the propagation direction. It's perpendicular. And here's the magnetic field direction. It's the third vector of a triad, k cross epsilon. So electromagnetic waves are transverse waves. They oscillate in a direction perpendicular to the direction of motion. The example we worked out last week had propagation in the x direction. So the wave vector was k x hat. And it had polarization in the y direction. So epsilon hat would be y hat. And k hat cross epsilon hat would be z hat. Forgot to write it here. It's x cross y is z. Now some properties of the wave. The phase velocity, that's omega over k, is 1 over the square root of mu epsilon. The index of refraction, that's the speed of light in vacuum, divided by, divided by the phase velocity. That's the square root of 1 over mu epsilon times the square root of mu 0 epsilon 0. And for example, Snell's law says n1 sine theta 1 is n2 sine theta 2. So these are the kind of equations we used last week. They come from geometrical optics. The textbook mentions Huygens' principle. Huygens was a Dutch physicist and mathematician, lived at the same time as Isaac Newton. Newton and Huygens had a big disagreement over the nature of light. Newton thought light was a stream of particles. Huygens thought it was a wave phenomenon. Here's a case where Newton was wrong. To describe waves, Huygens said that if you have a wave front, each point on the wavefront acts like a source of waves propagating away from that point. And if you add all those waves together, you get the next wavefront. So you have a plane wavefront and a plane wave. Wavelets, those little waves produced by each point on the wavefront. And then the new wave, after some time, delta t, it'll be propagated. It'll be propagated in the x direction, and it'll be a new planar wavefront. That's Huygens' principle. That's how Huygens viewed the production or the propagation of waves. Another thing that you can find in chapter 34 is a re-derivation of Snell's law. So Snell's law was derived in an earlier chapter using Fermat's principle, but using waves and wavefronts, the authors derived Snell's law by a geometrical argument involving wavefronts in refraction. As the ray diffracts, the direction of the plane waves, or the direction of wavefronts, remain perpendicular to the angle, to the ray. So you see the wavefronts are bent as they pass into the material with a slower velocity. Let's say this is vacuum, so they have the speed of light c. Let's say this is glass, so they have a speed of light less than c, c divided by the index of refraction. That means that the ray is bent towards the normal, and the wavefronts are also bent because they have to remain perpendicular to the ray. By analyzing the geometry of that process, one can derive Snell's law. All right, so now we've reviewed electromagnetic waves and geometrical optics, something we talked about last week. And now we come to interference. Interference is a consequence of the superposition principle. Maxwell's equations are linear. So linear combinations, that is to say superpositions, of solutions also solve the equations. So here's the theorem. The superposition principle is valid for solutions of Maxwell's equations. Well, what does that mean? If you have two solutions of Maxwell's equations and you add them together, that's a third solution. Or you can have any linear combination. You can have the first solution times a constant, plus the second solution times another constant. Add those together, that's another solution. So in fact, if you have two solutions, F1 and F2, because C1 and C2 are arbitrary constants, this gives me a whole infinite family of solutions to Maxwell's equations built out of the two basic solutions, let's say F1 and F2. And the proof of this is very simple. Maxwell's equations are a set of four linear equations. They have the form differential operators acting on a function, the function of the electric field, let's say, is zero. For example, del cross E minus dB dt is zero. So the field would be a combination of field of electric and magnetic fields. All right, so that's Maxwell's equations. Really stands for four equations. And it's linear. And here's another solution. The same operations, differential operator D, acting on some other function, f2 is zero. Now add C1 F1 plus C2 F2. Act on that with the differential operator. Well, because derivatives of constants are zero, the derivatives of C will give me no contribution. And the derivative of A plus B is the derivative of A plus the derivative of B. So this is just C1 dF1 plus C2 dF2, but dF1 and dF2 are zero. So this linear combination is also a solution of the linear Maxwell equations, the set of four Maxwell equations. So assuming that any solution of Maxwell's equations can be physically realized, we're led to this question. What happens when electromagnetic waves are added in a superposition? And the answer is interference. The waves interfere with each other. The textbook gives three examples, which we'll work out in the screencast. First of all, superposition is of plane waves with equal wave vectors. That is to say, K1 is equal to K2. The waves are traveling in the same direction. Well, if they're traveling in the same direction and they have the same frequency, aren't they just the same thing? No, because they can have phase differences. The phases may differ in position. And that will lead to either constructive or destructive interference. That will be our first example. Second example is two-slit interference. This is electromagnetic waves, let's say light waves, passing through two thin slits in a transparent material like a metal foil. So you have two slits in a metal foil, and you have waves hitting these two slits, but coherent waves. So waves in which the distance between the slits is small. That experiment was done by Thomas Young in 1801, and he observed constructive and destructive interference. This was really the historical proof that light is a wave phenomenon, because there's really no way to get interference like that if light is a stream of particles. This was after the time of Newton, so Newton never saw Young's experiment. If he had seen Young's experiment, he presumably would have understood that, yes, light is a wave phenomenon. Newton's influence was so great that many physicists in England, not so much outside of England, but in England, they are all listening to Newton too closely, and they didn't even understand Young's experiment. But to most physicists, it was understood that Young's experiment implies light is a wave phenomenon. And the third example is thin film interference, something that we can see in everyday life. An example with interference in everyday life. There's a similar phenomenon which is also described in the book called Newton's rings. In fact, Newton discovered interference in a device which we today call Newton's rings. But he didn't understand what it was. He still thought light was particulate. Constructive and destructive interference. Let's take the electric field, E0 sine kx minus omega t, in the y direction. So that will be E sub y. E sub y is E0 sine kx minus omega t. So that's the plane wave that we had last week. And let's add to it E0 sine k x plus delta x minus omega t, where delta x is small. It doesn't have to be small, but delta x is a displacement. So this is a displacement. You've just moved the position of the wave by an amount delta x. Now that's a superposition of two waves. They have equal wavelengths because it's the same k. It's the same kx dependence. Remember, the wavelength is 2 pi over k. So lambda 1, lambda 2, they're both equal to 2 pi over k. So the same wavelength, but there's a phase difference. This has a different phase compared to sine kx. Kx minus omega t, here you've added an amount k delta x. So there's a phase difference, k delta x. And now let's just plot these three waves, E1, E2, and E. So this gray curve is sine kx. So in other words, I'm taking a snapshot of the wave at time t equals 0. Well, here's a snapshot of sine kx at k equals 0. It's this wave. You see, at x equals 0, it's 0. And then it oscillates sinusoidally. Now what about sine kx plus phi? I've shifted the wave by some amount k delta x. Let's take phi to be pi over 3 and plot it again. Well, that's this wave. This gray wave is also sine kx, but it has a phase shift. So you see, it doesn't go through 0 at x equals 0. At x equals 0, and t equals 0, I'll have here sine pi over 3, sine of 60 degrees. That's the square root of 3 over 2. That's 1.7. No, 0, sine, let's see, that's the square root of 3 over 2 is about 0.8. So you see, it doesn't go through 0 at the same point in x. It's shifted over by an amount. This is the point where it goes through 0 at an earlier time, at an earlier or a point to the left of x equals 0. And of course, it oscillates then sinusoidally with the same wavelength. And now let's add the two gray waves, and we'll get the superposition. That's the red wave. Well, you see, it has the same frequency. It has a phase shift which is halfway between 0 and phi. And it has a larger amplitude. That's called constructive interference. The two waves interfere constructively, producing a wave with a larger amplitude. In other words, the electric field will be approximately twice as large as either of the individual waves. And remember, the electric field transports energy, and the energy transport goes like the square of the field. So if the field is about twice as large in amplitude, the energy transport will be approximately 4 times greater. Energy transport in an electromagnetic wave is the intensity. So this superposition will have a higher intensity by a factor of 4, approximately 4. If k were 0, not pi over, if phi were 0, not pi over 3, then the two waves would just be the same wave, and the superposition would just be 2 times either one of the gray waves. Then the amplitude would be twice as great. The energy transport or intensity would be 4 times as great. So that's constructive interference. If you add two waves, you'll get a bigger wave, but not just by a factor of 2. Well, the electric field increases by a factor of 2, but the energy transport increases by a factor of 4. Now let's consider where the phase shift is not pi over 3, but it's pi times 5 divided by 6. So again, this is sine kx, a snapshot at time 0. And this is the other wave at x equals 0, sine kx plus phi, where phi is close to pi, a little bit less than pi in this case. And now add the two waves. Well, you see, when you add the two waves, they nearly cancel. You know, where this wave is large, this wave is small. Where this wave is 0, this wave is almost 0. So when you add the two waves, you get something smaller. That's the blue curve. The blue curve is now the superposition. But it's a superposition of waves with a large phase shift, large meaning close to pi. In fact, if the phase shift were exactly equal to pi, then E1 would just be minus E0. Let's call this E1. And let's call this E2. If phi were 180 degrees, pi over 2, pi, then E1 would be minus E2. E1 plus E2 would be 0. So for a phase shift of 180 degrees, pi radians, you would have complete destructive interference. You would add the two waves and you would get 0. Now in terms of the electric field, that's not so hard to see, because you'd just be adding sine kx and minus sine kx. But in terms of the electric transport, that's pretty impressive, because one wave has electric transport E0 squared. The other wave also has energy transport E0 squared, but the superposition has energy transport 0. It's not because the energy transport of one wave is to the right and of the other wave it's to the left. The energy transport of the individual waves are both to the right. But when you superimpose those two waves, which are both traveling in the same direction, the result is nil. And so there would be no energy transport. That's called perfect destructive interference. Now in this diagram, it's not perfect interference because the phase shift is not 180 degrees, but it's close to 180 degrees. And so you get strong destructive interference. If you compared the intensity of either of the two waves, E1 and E2, you'd get a certain value. When they're interfering, you'd get a very small value, a much smaller value. So those are examples of constructive and destructive interference, and we'll use these examples in the next examples. The second example is two-slit interference. Let's say we have a wave, a plane wave, incident on an opaque material with a slit cut in it, like a piece of metal, a metal foil, let's say a little piece of aluminum foil, with a slit. So here it is with a front view. Here it is with a top view. So you're seeing it from above. What you see is an absorbing material here, an absorbing material here, or actually a reflective material here. That's the metal. But in the middle, you have an opening. So you have waves going through an opening. What happens on the other side of the opening? You might think, well, if waves go through an opening, they'll just come out in this direction, and this will all be in shadow. But that's not true. Not if the slit is narrow, a thin slit. So I really should say thin slits. If the size of the slit, if the distance or the length or the width of the slit is small, not much larger than a wavelength, then when the waves pass through the slit, they spread out. The spreading of waves that go through an opening is called diffraction. So the first figure here shows diffraction. As light passes through a slit, it spreads out. In other words, if you were standing here and the light is going through here, you might think you wouldn't see it. You might think, well, you're in the shadow. But actually, you would see light coming in this direction. It's a little hard to believe that for light because the wavelengths of light are so tiny, but it's very easy to believe that for sound waves. Suppose you have sound waves coming in from one place, and then a doorway, and then another room. So we have sound waves going through a doorway. If you're standing right in front of the doorway, you'll hear the sound waves. But if you're standing by the wall, you'll still hear the sound waves because the sound waves undergo diffraction. As long as the size of the opening is comparable or smaller than the wavelength of the wave. So we'll come back to diffraction in the second part of the screencast. But anyway, for now, we'll just say as parallel rays, which is to say coherent planes, pass through an opening, they spread out. And they form, the opening is like a source, a little point-like source. It's kind of like Huygens principle. Huygens principle says in order to get the next front, you propagate waves from every point on the previous front. They don't travel in the direction, the wavelets don't travel in the forward direction. The wavelets travel in all directions. But when you add all the wavelets together, you get a new planar wavefront. Well, if you do that same thing where there's an opening, the wavelengths for the portion of the wave approaching the opening will spread out and form, I guess, a circular wave. If this is a slit, you view this in 2 dimensions, you'll have an outgoing circular wave. All right, well, let's take that as given, and now let's consider you have 2 openings. Well, the wave on the right side will be a superposition of circular waves from one opening plus circular waves from the other opening. Now, when the 2 waves cross, that's a point of constructive interference. So you see, you'll have directions where you'll have constructive interference. So for example, in this direction, I guess coming back here, there'll be everywhere along that ray constructive interference, high intensity. And similarly, along in this direction, you'll have constructive interference because the two waves, their maxima are occurring at the same place. So if you think back to the previous example, where the maxima are occurring at the same place, they have the same phase. So it's two waves in phase. That's constructive interference. Well, you see, you'll have certain directions with constructive interference, and in between the regions of constructive interference, you'll have destructive interference. So you get an interference pattern. So if you looked at the light far away on a screen, so here's a little projection screen, and you looked at the light emerging from this set of two slits, you'd find, well, at the very center there'd be a bright fringe, and then there would be a succession of bright fringes where the intensity is large. Those are the directions of constructive interference. So it only works if the incoming waves are coherent. An example of that would be laser light. Laser light is coherent. That is to say, all the wave fronts line up. All the planar wave fronts are parallel. And so all of the waves coming out of the two openings are in phase. Then the outgoing waves, or the waves going in the front direction, will interfere constructively in some directions and destructively in between the bright fringes, so for other directions. Now in the book you'll find the equation for constructive interference. D sine theta is m lambda. So that's theta. It depends on m. M is an integer. So m in these equations could be 0. It could be plus or minus 1. Plus or minus 1. It could be plus or minus 2. Plus or minus 3, etc. So here is the central fringe. That's m equals 0. Here is plus 1 and minus 1. That's the nearest fringes to the side. And here is plus 2 and minus 2. So those are the second order fringes. So we have the 0th order fringe, the bright region in the angle 0. And then we have the first order fringes on either side, and we have the second order fringes on either side a little further away. And the angles are given by this equation. D sine theta is m lambda. Lambda is the wavelength of the light. D is the distance between the slits. So this distance D, this distance is D. What about the width of the slit? Well, we're assuming that the width is very small. These are called thin slits. So the size of the slit is assumed to be very small, small compared to D. So the size of the slit doesn't matter. The answer only depends on D. So D sine theta is m lambda. And in between m lambda, m and m plus 1 lambda, at m plus a half lambda, that will be destructive interference. So you'll have an alternating set of bright regions and dark regions. In fact, if you read a little further in the chapter, there's a formula for the intensity as a function of the position y on the screen. So here's the screen. Here's the position y. And the intensity goes like the cosine squared of y. So in other words, the intensity pattern, intensity as a function of y, it'll go like cosine squared. So you know what cosine squared looks like. It oscillates between +1 and -1. So you see you'll have an oscillating or an alternating pattern of bright fringes where cosine squared is equal to 1 and dark fringes where cosine squared is equal to 0. So this is an equation in the book if there's a line kappa problem which asks for intensity in two-slit interference, you'd use that equation. The problem might not ask for the intensity at all values of position on the screen. It might just ask for where are the positions of the bright fringes. Those would just be the maxima. The maxima of intensity will be the bright fringes. Okay, so those were two examples. No. Those are two examples, if you're taking notes. All right, we've gone over two examples. The third example is thin film interference. Suppose you have a piece of glass and air on two sides of the glass. And suppose you have an incident wave. So the wave will hit this surface of the glass. Part of it will be reflected. So here's the reflected wave. So this is the reflected wave for the first incident wave. But part of the incident energy will be transmitted into the glass. There'll be refraction. And it will hit another surface. Part of that will be reflected. Part of it will go out into the air, but we're not interested in the part that goes out into the air. We're interested in the part that's reflected. And then when it reaches the glass surface again, part of it will be transmitted through the glass. That will be the second reflected ray. So you have one incident wave, you have two reflections, they will interfere. So here's a figure from the textbook. Light waves in air, incident on a thin film, I said a little piece of glass, but it could be a little film of any material. It could be a little film of oil, for example. With index of refraction n and thickness t, so this thickness is t, there'll be a reflected ray from the front surface, and there'll also be a reflected ray from the back surface, and those will interfere. So the outgoing light will show interference phenomena. Here's the equation for thin film constructive interference. m plus a half. Again, m is an integer. So m is 0, 1, 2, 3, 4, and so on. Lambda is the wavelength in air. The wavelength in the glass is a little different. So you have the wavelength in air divided by the index of refraction of the glass is 2 times the thickness. So T here is the thickness. So I won't go over the derivation of this, but you can find it in the textbook. It's the condition for constructive interference for reflection of light from a thin film. Now, the related phenomenon called Newton's rings, here's a little Newton's rings demonstration. It consists of a plate of glass and a plano-convex lens. So there's a lens where the top is a plane and the bottom is a section of a sphere, a hemisphere or a semicircle, well, spherical. And then it's resting on top of a plain plate of glass. If you have light incident from above, part of the light will be reflected from the convex surface, that's R1. Part of the light will be reflected from the surface of the glass, that's R2. Now there's some other reflections going on here, but these are the two that are important. So there's incident light, various reflections, but in particular there's part of the light will be reflected from the circular part, the convex part of the lens. Part of the light will be reflected from the upper surface of the glass. Those will interfere. And so if you look at this picture very closely, if I blow it up a little bit, you can see the reflected light incident on this combination of a plano-convex lens on top of a plate. You see you get interference pattern. At some angles you have high intensity, at some angles you have low intensity. So some of these are the constructive interference, some are the destructive interference. Now, why do you get the colors? Well, because the condition for constructive interference depends on the wavelength. In fact, the radius for constructive interference, the radius for a bright region, a region of constructive interference, is given by this equation, the square root of r, m plus a half lambda. Depends on lambda. So it's a different radius. This is really a radius. It's a different radius for red or for violet. So the interfering rings, or the interfering light waves, form rings which are like little rainbows with a variation between red and violet. And you see there are multiple rings corresponding to different values of m. So there's m equals 0, m equals 1, m equals 2, m equals 3. There are rings of increasing radii as m changes. So these two examples are described in more detail in the book. I won't go over them in the screencast, but you may have line kappa problems where you have to apply these formulas. All right, well, there's another part to the screencast which has to do with diffraction, and so there will also be questions about diffraction on the log kappa assignment.